Can I go? Okay, so welcome everybody. My name is Luca, and today I will give some update regarding my research about emissive Langmuir probe theory with application to lower function tether that I'm doing here, supervised by Professor Gonzalo Sanchez-Arriaga. I will start with a brief introduction in which I will recall what lower function tethers are and what is the problem that we are trying to handle in and how we have dealt with it so far. Then I will speak briefly about a novel solver that we have been developing in order to expand the range of analysis that we are able to address. Then I will present some of the latest results that I've been collecting during the latest months before giving an overview of the main contributions and speaking about what is the plan for the next future. So let us start by recalling what lower function tethers are. So as you can see here from this nice snapshot, lower function tethers are basically long conductors that have been proposed as an effective way to deorbit satellites at the end of life. Basically, how they work is that once the satellite reaches the end of its mission, the tether gets deployed, and as you can see here, it starts interact and exchanging electrons with the ionospheric plasma. These electrons are basically collected at one end, and if we cover the conductor with a lower function material, they can be emitted back at the other end of the tether, therefore generating a stable current here. And the presence of these currents in presence of the magnetic field basically give us a drag force that we can exploit in order to deorbit the tether satellites ensemble. Of course, you can imagine that in order to be able to assess the tether performance, we need to properly model this interaction of the tether between the tether and the plasma. And we do that by exploiting the fact that each section of a tether, given its geometry, can be modeled as a two-dimensional probe that is facing the same plasma as the tether and that has the same geometry as the one of the tether. Now, so far, in order to do that, we have developed therefore our two-dimensional kinetic model for emissive probes, in which we have our probe, which is immersed in an unmagnetized collisionless Maxwellian plasma. And so far we have considered only stationary conditions. Therefore, with this set of hypotheses, let's say we are not able to take into account and to measure the impact of the trap particles population on the sheet that develops around our probe. Now, according to this set of hypotheses, the sheet is described by the stationary Vlasov-Poisson system of equation, which is here, a solution of which is determined by these 6 non-dimensional parameters in which appear the geometry of the probe, the bias, characteristics of the plasma species, and the emission level. And of course, we have also to impose appropriate boundary conditions. To solve this problem, last year I already presented a first code that we have developed that goes by the name of FONX-G, which basically solves iteratively this Vlasov-Poisson system by updating the space charge density according to this Newton method map. So the code was verified, it was also registered in Registro de la Propiedad Intelectual de la Comunidad de Madrid. But as I said before, it has a limitation in that it cannot address the population of trap particles, which is something that we are interested in pretty much because we think that they can have, we want to see if they have an impact on the final sheet that develops around the probe. Here what I'm showing is, for instance, a detail of the velocity space distribution function that I obtained with my stationary code here on the top. I detect that there are some trap particles, but I cannot, let's say, disclaim where they come from. So in our model, we tend to neglect this, and this gives me this green profile here for the attracted ions. But what would happen if instead of setting the distribution function to 0, I would assign them a finite value? Then you can see that a bump would appear in the sheet, and we want to see how this can, let's say, affect to the sheet that develops. So in order to do that, lately I've been working on trying to develop a new solver using a semi-Lagrangian approach. So basically, pretty much this is the updated model in which we have relaxed the hypothesis about the steady state of the solution. And therefore, we are able to assess the role of trapped particles. We have some modification to the equation, and also it appears here a new governing parameters, which is basically the ratio between the mass of the ions and that of the electrons. And yeah, to do that, of course, I had to implement some changes in my already existing code. As I mentioned before, we are following a semi-Lagrangian approach, meaning that we are updating, well, most of the changes were related with the Vlasov solver, and therefore to the computation and to the update of the distribution function. And we are following a semi-Lagrangian approach, meaning that we are updating the distribution function through a backward integration of the Vlasov characteristics. Pretty much here, well, here you have a nice sketch that I taken from this article in order to illustrate how this works. So imagine that at a certain point in our domain and at a certain time step, I know what the distribution function is. Now, in order to update the value of the distribution function there, what I can do is to perform a backward integration and see where the characteristics of the Vlasov equation end. So I will obtain, let's say, the root of these characteristics. Now, given that the plasma is assumed to be collisionless, the distribution function we know that is conserved along these characteristics, and therefore, knowing where the let's say where the root of the characteristic is, there are three possible cases. Either the origin of the characteristic is at one of the boundaries at which we know the distribution function because we're imposing it through boundary condition, or it ends up inside our domain and in a point that in principle does not coincide with any of our nodes, and therefore we can compute the value of the distribution function there through interpolation. Now this value, of course, at the origin of the characteristic, assuming a collision in plasma, will be the new value of the distribution function at the node of my computational domain. So far, we are currently under verifying this new code, so I don't have still, I mean, I have some preliminary results, but there are some things that we are still looking into that. But yeah, but besides that, in parallel, I have also carried out some parallel activities, some parallel analysis. First of all, I have exploited the fact that I spent 4 months doing a research visit at the Los Alamos National Laboratory, where actually Pedro is now. And there I had the opportunity to use CPIC, which is a particle in cell code that was developed by the group of Dr. Delzano there at the Los Alamos National Laboratory in order to study plasma material interaction in presence of curvilinear geometries. So on one side, what I did was to reproduce some of the results that I already obtained with my stationary code, funcsg, in order to provide some new verification for my code. Here you can see an example. So this is the configuration that we are considering. And here on the right, I am plotting the plasma sheet at the horizontal axis of this computational domain. And as you can see, the two codes are in well agreement. In particular, they also detect and agree very well in detecting this potential well that develops at the probe as a consequence of the high emission level that we are considering in this case. Besides that, I've also started trying to assess the role of the trap particle with CPIC. So what I did was to reproduce the same simulation with CPIC using two different initial conditions. So the first one, the blue one, is by, let's say, assuming that the computational domain is empty, so assuming a zero distribution function everywhere, while the other one is putting a Maxwellian distribution everywhere. And as you can see in the first case, we do not detect actually any trap particles, but in the second case, there appears here this bump, which is similar to the one that we would expect, if that region of the distribution function would be full instead of empty. I've started also playing a bit with the electron emission, and as you can see, as the emission grows up, this bump actually is enhanced to the point where basically the density of the ions becomes higher than that of the background plasma. And an interesting thing that we can see here is that the potential well developing at the probe is actually less severe in the presence of this trap population, which might suggest that in presence of trap particles, we would have, let's say, a delay in the onset of the space charge limited emission, which is something that could be interesting and also useful for a Tether application. Now, well, of course, these are just preliminary results, but I'm still looking into that. And before concluding, just a brief overview of the contributions. So these this is where I was at the past year. In this year, we've published a second paper at the end of 2021, and we are also waiting and are in the process of a review of a third one, even though this is more related with emission analysis rather than this plasma-theta interaction. Regarding conference, I will attend the 48th EPS conference in plasma physics, which will be in 2 weeks with a poster session. And besides that, I've already spoken about the software registration. I'm still involved in these two projects, ETPAC, which is actually about to end in the next months, at the end of November. And I was also involved in BMOM. Then, as I said, I spent my 4 months working with the group of Gianluca Del Zanno at the Los Alamos National Laboratory. And regarding the next future, well, pretty much what I'm trying to focus on is to get the thesis done and to defend it as soon as possible. This was all from my side. Thank you very much for listening to me.